Well, welcome back, everybody. Hope everyone had a good weekend. Uh, there's a couple things I want to share with you first. Let me go to the calendar just to make sure we know everybody's in the right spot as far as knowing what's coming up. So today's the 9th. I did move some homework around because we're just starting chapter 9. So I moved homework chapter 9 to the 12th, and then the activity for 5 and the homework for 5, I moved that to next week on Wednesday. And then the activity for 6 and homework for 6 on the 20th and 22nd, respectively. We have scheduled right now exam number 2, which is chapters 4 and 6, scheduled for the 23rd. So that's our tentative schedule. I think we'll be okay time-wise to make that date. All right. So the other aspect I want to share with you is the numbers. Okay, there was a question, and let me do a comparison here. And let's just say I have the number 300. Got some people coming in. Come in. Okay. The number 300 versus 300.0. Okay. Now, with respect to these two numbers, the numbers here with respect to value are the same. Okay. Now they're the same because put a dollar symbol in front of there. If I were to give you $300 with the first number or with the second number, I'm still going to give you $300, right? It's the same number. It's the same value. So these numbers have the same value. Where they differ is in the accuracy. Now, the first number, 300, that last number, which is the 0, is in the ones position. That is the number that has uncertainty. Okay, so if we were to measure that with some material, then that number would have an uncertainty that can range. It could be from 299 to 301. Okay, so we have a big range here of roughly 2 units of whatever this number represents. So it goes from 301 to 299. So we got a range of 2 units. Okay. Now, with respect to the other number, this true value, and I state the true value because, first of all, there's nothing with respect to measure. There's no number that is, say, accurate that is measured. Okay. There's no such thing as an accurate reading because every tool that we have out there that measures anything, length, mass, volume, has a degree of uncertainty, and it's always that last digit. Okay. Yes, there are exact numbers, like a dozen, there's 12. That's an exact number. But when it comes to measurements, nothing's exact. So the point being that this reading here could vary from 299.99 because that last number is the one with the uncertainty. So it could go that distance. So I have roughly, 2 units again, but in the 10th of a unit. So you notice that the first number, 2 whole units. The second number, as far as the range, could be 2/10 of a range, 2/10 of a unit. So the second number offers more accuracy. It doesn't offer more value because those numbers 100 is still 300. But the second number to the 10th place offers more accuracy because we measured it with a tool that was a lot more accurate than the first number that we may have measured with, I don't know, a simple ruler. Second one we could have measured, if this is length, we could have measured maybe with a laser beam and get us to the 10th place. Okay, So that's the difference here. That's the difference with respect to numbers, is that yes, those 300 and 300.0 are the same number with respect to value, but they're different with respect to accuracy. Okay. All right. Let's go back. So here we go. Let's go back go to chapter 5. All right. So up to this point, we talked about the model of the atom. The work done by J.J. Thomson and Rutherford demonstrated that two things. One, the atom consists of a nucleus where the proton and the neutron reside. Okay. And two, the electrons are somewhere in that atom. Well, up to that point. So we all pretty much are okay with the nucleus and the neutrons and electrons being in there. But up to this point, we're quite sure where the electrons reside. So it required obviously more data, more information. But remember this, that the electron with respect to size is extremely small. So its atomic mass unit is essentially 0. Even though it's 0 and it's almost massless, it's not massless, but it's so small that it behaves like a light wave. So we need to talk a little bit about the light wave, because in light, we know that light has specific energy values. Okay. So let's talk briefly about wavelengths, because this is how the electron is behaving. Now, we have this red diagram here, the blue, that represents a wave. Now, if we take that wave and we are able to mark a spot, say, on top of the hill, notice this wave consists of hills and valleys. Okay. Now, if we mark a spot on top of the hill, for example, and if we go to the next hill and mark the same spot, we can measure that. And that's the length there. What we have is this symbol called lambda, the Greek symbol lambda, which represents wavelength. That is the wavelength of this particular image. That's the length of that wave. Okay. Now notice I picked the top of the hill, but keep this in mind. You can pick the bottom of the hill as long as you're picking the bottom of the hill in the next wave. Or you can pick any spot, say on the right shoulder, but pick the same spot on the next wave. That distance is still the wavelength and is denoted by that symbol lambda that says that is the measure of the distance between peaks or points between waves. Okay. Now the frequency, and you're probably used to this term, frequency, because right now, if you're on a computer, your processor is working with a certain amount of speed. You may have a 2 gigahertz computer or 1 gigahertz, whatever the case may be. Giga meaning billion. If you got a 2.0 gigahertz computer, you are doing 2 billion things in 1 second. The frequency, which is denoted here by this symbol, looks like a V. Okay, it's really mu, mu, the Greek symbol mu. That is frequency, and that is the number of wavelengths, the number of things that happen within 1 second. Okay, and so your example of the computer with 2 gigahertz, there's 2 billion things occurring to your computer in 1 second. That's pretty fast. Pretty fast. All right. So with that in mind, we got wavelength and frequency. If we compare these two different wavelengths, we take a look at the top one. First of all, you can see the wavelength when we compare the wavelength of the top image with the bottom. The top wavelength is much longer than the bottom one. So the top one has a long wavelength, the bottom has a short wavelength. Okay. When you have long wavelengths, you have low energy. Classical example is your radio waves when you're listening to the radio station. Those wavelengths are like 1 meter, very long, very big, low energy. Okay. The opposite of that would be things like X-rays. X-rays, for example, have very short wavelengths, a lot of energy. They're very powerful. They go right through your body. Hence, we can take X-ray images of your body or other things. Okay. And so when we have a wavelength that has a long wavelengths, we end up having low energy. So long wavelengths gives us low energy and gives us low frequency. Okay. Meaning, for example, what if we designate 1 second time period between these two lights right here, the two lines right here? That's 1 second. You can see in the top wavelength, maybe about one wavelength passed in that 1 second time interval. Whereas at the bottom one, you probably looking like two wavelengths. So two wavelengths occurred within that one time frequency, 1 second frequency. So it would have a high frequency compared to the long wavelength that has a long frequency. Got too much stuff going on here. So low energy implies long wavelengths and low frequency. High energy light, short wavelengths, high frequency. Okay. If you ever get a graph that says, okay, which wave has high energy, which has a lower energy, you can see that the short wavelength here, lambda b, would be high energy. And that implies that A, the low frequency. Okay. So by being able to look at a graph and determine who's has higher energy, who has lower frequency. Now this whole wavelength thing this is what we call the electromagnetic spectrum. Okay. Now on the far left, we have gamma rays, but even above that, even further to the left, we just keep it at gamma rays right now. Those are very powerful wavelengths. Okay, extremely high energy. To the far right, you have radio frequencies, very big wavelengths, but very low energy. Now, the scale here is not, this graph here is not the scale, the spectrum is not the scale, but our eyes can only see a very small amount. It's kind of skewed a little bit, makes it look like we can see a lot as far as the whole wavelength, but we can't. That is what we call the visible wavelength. Our eyes have cones and rods in our eyes cells that are able to pick up color and grayscale. That's about it. Behind us or below us are the infrared and microwave wavelengths that have lower energy, but they're below the visible. Above us, we have UV, ultraviolet, much stronger than visible. Ultraviolet can be very hazardous. That's why you're out in the sun, you want to have a blocker because UV light can cause all kinds of skin damage. All right, so big spectrum, gamma rays on one side, radio waves on the other, visible, very small amount of what we can see. And that is the whole electromagnetic spectrum. Okay. Now, in the previous chapter, we were talking about J.J. Thomson and the other scientists. Remember, there were the 1900s. Well, in the same time period, again, this one other scientist called Max Planck, another famous scientist, very famous. There's a Max Planck Institute in Europe named after him, physicist. He proposed a very controversial idea during this time period. He believed, now we're not talking about electrons, right? We're going to take the theory about light and energy and apply it to electrons here in a second. He proposed that energy was not all continuous, but actually was emitted in small bundles. Those bundles of energy he called quanta. Okay? And that he also proposed that energy with respect to electromagnetic radiation was not continuous. It is very specific. It's a very specific amount of energy. Okay. He defined that energy of light as a photon. And so that's where Star Trek gets its photon torpedo business. Okay. Anyway, Somebody has their speaker on. You may want to mute yourself. I'm picking up reverb. All right. So what he's proposing is that energy exists in levels, not continuous. And we can do an analogy with respect to this ramp and the stair step. Now, prior to this, energy was thought as to be continuous, like this ramp. Okay. What he has proposed is like the stair steps. You start at the bottom of the step. That is your ground state. That's ground zero. With that itself, with an X amount of energy. And when you move up, you have to go a specific amount of energy. Okay. There's more of a stair step. So that's Max Planck's contribution. So here comes a chemist / physicist. His name is Niels Bohr. Given the smallness as far as the electrons are concerned, he proposed that electrons must occupy very distinct energy levels. That's what his proposal was. Okay. And that electrons themselves are quantized. Okay. And that they orbit around the nucleus, much like our planets do around in our solar system, but three-dimensionally, okay, not just one-dimensionally like the orbits of the planet, but they could be in different areas in the 3 X, Y, and Z position. These orbitals, he called them energy levels or shells. All right. Now, if you look at the periodic table that we use, what I've done here, if you haven't done it, you might take a pencil and starting with hydrogen and working your way down the column, you have 7 levels. Okay, we call those periods go across. So period number 1 goes from hydrogen to helium. Okay, period number 2 encompasses lithium across to neon. Okay, and then let me pick another color here. Period number 3 starts with sodium and works a way across to argon, and so on down the road. There are 7 distinct energy levels, and the periodic table denotes them by the numbers 1 through 7 down the periodic table, and those are distinct energy levels. Now, just like layers of an onion, start with the first layer and then just work your way up. Now, with that in mind, if you needed to take an educated deduction on this, the radius of these atoms, what could you say? Who's bigger, lithium or cesium?
Cesium?
Exactly. Cesium is bigger because cesium, its whole size, its electrons, its outermost electrons occupy the 6th energy level. So you got your first trend in periodic table. That is, you go from top to bottom, the radius of the atoms get bigger. Okay? They get bigger. And we'll learn when we go from left to right, we'll learn more about that trend, which is counterintuitive, but still not too difficult. So going down the periodic table, just by the sheer fact of the energy levels, the atoms get bigger. All right. So going back here. Now, each orbit has a specific radius and a specific energy. And there's obviously a certain distance from the nucleus. And we denote them by these dotted lines. If I showed you, I think I did show you the build the atom simulation, where you grab the electrons and they had a dotted line that represents the orbits. Here represents 3 energy levels denoted by the dotted lines where the electrons occupy. Now, how do we know this? You know, what data do we have? Well, we have what's called line spectrum. Okay, let me explain what happens there. That if you take, and you've seen this around you, you've seen fluorescent bulbs. They light up, right? You know, you get a fluorescent bulb, you business in the office or maybe at home, plug it in and it lights up. Well, that fluorescent bulb has in it a gas, and you run electricity through that bulb. Well, that bulb, that electricity excites the molecule of the gas in there, excites it. Well, uh, once you picks up that energy, it doesn't hang out at the excited state very long. It's counter nature, if you will. Atoms, molecules, they get to an excited state, but they have to drop back down. Okay. And when they do that, they have to emit the energy that they absorbed, and they emit that energy as light. And so the fluorescent bulbs that you see is what's the light that you see is due to the excitement of the molecules in the tube. They're going back to the ground state, and they're going, and that light is of a specific energy, very specific amount. We can do this for a number of materials, and we end up what's called an emission line spectrum. How does that work? Well, let's take a look at it. We got the tube, just like the fluorescent bulb. The only difference is, in this case, we're going to put hydrogen gas in it, but you can put in multiple things in it, okay? And then we excite it with electricity, hence the electrical cable hookup there, the dark color. We run it through a slit, and the slit, all that does is focuses the light. Then that light goes through a prism. Now, you're familiar with prisms, if not in science in high school or wherever else. But next time it rains, you go outside, you see a rainbow. Guess what? You see a prism out there because the water droplets have taken the light, which normally is white light, and white light consists of electromagnetic radiation of multiple wavelengths, and it breaks them up. Okay, and that's what the prism does. It takes that light of the hydrogen material and breaks it up into their own specific wavelengths, and you end up with the spectrum here. Each line has a specific wavelength. The units, nm, those are nanometers, 10 to the -9 meters, okay? Now, the neat thing about this is that you can do this for a variety of different things, elements, compounds. And guess what? Each one has their own unique emission line spectrum. That's how we can identify what's out in space, 10 billion light years away. We analyze the light, break it down, and we can figure out what kind of materials out in space, okay? So each compound, each element has their own specific emission line spectrum. And each line there, we can back calculate, we can figure out with respect to their electrons and what levels they're at, okay? So this tells us that the spectrum tells us that these electrons are in specific energy levels. Like I stated before, if you look at this diagram, here's an example of the nucleus and an electron. You energize it, it causes that electron to go from here, in this case, the inner energy level to the next energy level, okay, of specific amount of energy. Now, nature being nature, Mother Nature being Mother Nature, is not going to stay there forever. So it needs to come back down to this ground state. And when it does that, it needs to release the energy it absorbed when it went to the excited state. And it does that by either giving up heat and light, or a combination thereof, both heat and light. The old, and that is designated by this arrow with a little squiggly line that represents light being emitted. The old incandescent lamps, they got pretty warm. You grab them, right? You grab them, they're so hot, but they give you light. They give you heat and light because they're releasing the energy that they accepted to go into the ground, into the excited state. If you have an electrical stove at home, you're seeing what's happening there. You got a material, you got electricity running through that coil of metal. And the atoms are getting excited by the electricity, and then they got to emit that electricity, the electricity, the energy they absorb, they're going to emit it. But in the case of the coil, they emit it more as heat. They do give off a little bit of light. That's hence the redness of the coil. All right, so that's what's happening here. Now, all this theory is based on a lot of mathematical equations, which is beyond the scope of CHM-130. But based on that information, it was proposed that there are 7 energy levels. Now, right now we have 118 elements. Okay. Given the trend that you observe in the periodic table, okay, if we were to discover element 119, where would you predict it to be with respect to the energy level?
I would think it would be on the 7th or 8th energy level.
Yeah, because if you look at the trend here, let's take neon. It's a good analysis here, but let's break it down here. Okay, let's look at argon. Okay, it is in the 3rd energy level. Okay, it's number 18. Now, number 19 is potassium. Look what happened to it. It went to the 4th energy level. We go across the period to krypton, good old krypton, number 36. And when we find number 37, guess where he went? To number 5. So number 118 is right there. It's in the 7th energy level. So we would anticipate that when 119 comes around, we're going to have to create a whole new number 8 energy level. And it's going to be right underneath here. It's going to have 119 electrons, and one of them is going to be in the outermost shell. But we'll say a lot more about that here in a second. Okay. So there's 7 energy levels. Now, further theory gives us what are called sublevels. Okay, that within these levels there are sublevels that are named orbits, and we're given the name orbits. So you might see the name sublevels, but you're going to see the word orbits much more so than sublevels. Of these sublevels, at this time there are 4, and they've been given the symbols S, P, D, and F. Now, I don't know why they give him the letters P, D, and F, but the first one, S, it makes sense when we talk about the shape of it, because the S shape are round like a ball, so this sphere. The P shape is totally different kind of shape. I'll show you that in a second. And the D's and the F, there are some crazy looking orbits that have been defined. But that's where we're at right now. We've got the S, the P, and the D, and the F orbits. These are sub-levels of the energy levels 1 through 7. Okay. Now, the first energy level, the first period, there's only one orbit, and that is called the S. Hence, we put the 1 in front of the S, represents what period they're in, what energy level. Okay. And there's only one suborbit, one orbit, that's called the S. The second energy level, and I'm going to refer back to the periodic table here in a second, but we continue this, but I'm going to talk about this first, because you're going to be able to look at the periodic table. I keep referring to it lots of times for a lot of things, but we're going to be able to look at it and pick at least anywhere the first 20 and be able to tell you the electrons and where they're at, as far as what orbit they're at, what level they're at. We call that the electron configuration. We'll be able to do that just using the periodic table. On the 3rd energy level, keeping track, we're going down the periodic table. There are 3 orbits. We got the S, the P, and the D. And then the 4th, we introduced the 4th one, which is the F. So we got the S, the P, the D, and the F. Then note the trend here. When we're talking about the orbits, all of them have an S. Okay. Now, they just happen to be a different diameter. We're in the first energy level, so we got the first S. So we got a small, maybe the size of a marble as an analogy. And then the 2S, maybe the small size of a golf ball. And the 3F, maybe relative to the size of a baseball. And the 4F, maybe the size of a softball. And 5S, maybe the size of a beach ball. Okay. So they're all the same shape, they're just bigger in diameter. Okay. Now remember, the first energy level has no p orbits or sub levels. The next level, the T, that's where we introduce the P, the second energy level. So from 2 down, 2, 3, 4, 5, 6, and 7, they have the P orbits also. Okay. Now that 2 in front of that letter represents the energy level, that coefficient. And then the third, the D orbits are introduced. Let me get a different color here. In the third energy level. So we introduced the 3D and then the 4D, 5D, 6D, 7D. And then finally, the F is introduced in the fourth energy level. Okay, so 4, 5, 6, F energy level. So that is the trend. Now, keeping in mind the orbits S, P, D, and F. Okay, I refer back to the periodic table. Now you can take that periodic table and for the first two columns, think of those as the S elements. Hence, I wrote up there in blue, S elements. Think of them as the S elements. Okay. And notice how many columns we have in the S elements. Are there not 2 columns? Right? Okay. Keep that in mind. Now, over to the far right, starting with boron. I've highlighted in yellow. Okay. Think of these guys as the P element. Now, who can tell me how many columns you see in the P elements? How many columns across you count?
6 of them.
You got 6 of them. Keep that in mind. So 2 columns in the S, 6 columns in the P. All right. Let me do a different color so we can make sure we don't confuse anything. Now, within here, within the what I've highlighted here, starting with the 3B, going across here, think of those guys as the D elements. All right. Now, how many columns do you see there? How many?
10.
10. Okay, exactly. So I'm going to rehash. The S elements, 2 columns. The P elements, 6 columns. The D elements, 10 columns. All right. And then finally, make sure you're a different color. Going from here, starting with 58 across. Think of those guys as the F elements. And if you count those, you're going to find 14 columns. Okay. So the S has 2 columns. The P has 6 columns. The D has 10 columns. And the F elements have 14 columns. So as we go from left to right, the first column, starting with hydrogen on down, we can say 1s superscript 1. Second column, we can say well, if we're at the second level, 2s superscript 2. Okay. If we're at the, say, number 5, there'll be P1, go across to number 10, there'll be P6, P1, P2, P3, P4, P5, P6. The D, same scenario, D1 to D10, superscript that is number, and the F, F1 to F14. Okay, now, keep that in mind. All right. Clear this up. All right, so again, these are the first 4 levels, the first 4 energy levels. In the very first one, only the S show up. The second one has S and the P. The 3 has a 3 is the SP and the D, and finally the last one, SP, D, and F. Okay, we're only going to stop at the 4. Now, these orbits or sublevels are regions in space. Now, what they are is mathematical equations. And like I stated, we're not going to talk at length about these equations. These are quantum mechanical mathematical equations. But if you take an equation and you plot data, you generate some data points, you can plot that and you get a three-dimensional model of what that orbit looks like. So these mathematical equations describe the orbit, and then we plot it, the data, and it gives us an idea of what they look like. Now, every orbit can handle a maximum of 2 electrons, okay? Every orbit, every S can handle 2, every P can handle 2, every D can handle 2, every F can handle 2 electrons. But there's a different number of orbits. There's only one S, there are 3 Ps, there are 5 Ds, and guess what? There are 7 Fs. Okay, so the S orbit, there's only one S, and that can handle 2 electrons. The P orbits there's 3 of them, and each one can handle 2. So there's a maximum of 6 electrons for the P orbit. The D, there are 5 orbits. Each one can handle 2. It gives you a total of 10. Notice that the columns we were talking about earlier, remember the S elements had 2 columns? Remember that? Remember the P elements had 6 columns, and the D had 10 columns, and the F elements had 14. So we're going to relate all that to this that we're just talking about here. Okay. All right. So I wish this slide was upside down, because this is really, you really take this and put it upside down like an upside down pyramid, because you start at the bottom first. When you start adding your electrons, you start at the bottom. So you're level 1. Okay. Now, every box represents an orbit. And like I stated, every orbit can handle 2 electrons. So I'm drawing an arrow to represent an electron. So if you look at hydrogen, hydrogen has 1 proton and 1 electron. Okay. And if I go across the periodic table, I go to helium. And how many electrons does helium have? It has 2 electrons. Okay. So once I'm done with helium, I can designate this level as, let me make sure I get there. Okay, because the first level is done. 1 represents the energy level, S represents the orbit, and then superscript 2 represents the number of electrons for that. So helium has 2 electrons, and those 2 electrons are in the first energy level, and they are in the S orbit. Okay. Now we're going across the periodic table. So if you have that periodic table in front of you, you can follow along. So I started with hydrogen with 1 electron. That's 1s1, superscript 1. Then I shot across to helium, to element number 2, that has 2 electrons. So now its electron configuration is 1s superscript 2. Now to get through element number 3, which is lithium, I go all the way around the periodic table. I go back to the beginning, right? Guess where lithium is? It's in the second energy level. And it only has 3 electrons. So the first 2 are full, but in the second energy level, I can put 1 electron. You notice that? 3 electrons. Okay, 3 arrows. That's lithium. That its electron configuration would be not only 1s2, but since I'm in the second energy level, it is 2s superscript 1. That's lithium. Okay. Now, here's the other thing about these groups. Everybody in these groups have the ones at the A elements, 1A, Roman numeral 1A, 2A, across to 8A. Okay. They have something very important in common. Everybody here, okay? Everybody here has one of their electrons in the outermost shell that we call the valence shell. So hydrogen only has one electron. So in the outermost shell, there's one electron. Lithium, the one we just did, has 3 electrons, but one of them exists in the second energy level, in the 2s1. Okay. Sodium has 11 electrons, but of those 11 electrons, one of them is in the 3s1 orbit, all by itself. Next one down, potassium. Guess what? How many electrons does potassium have? 19. Of those 19, one of them is on the outermost shell. We call that the valence shell. It is in the 4s1. Notice the what they have all in common is on the outermost shell, they have 1 electron. And that is why they are in that same group, because they react very similar. Lithium, sodium, potassium, number 3, number 11, number 19, they have 1 valence electron. And because they have 1 valence electron, their reactivity is very similar. Remember, that's where all the action happens, chemical action. It's in the outermost shell, the electrons. Okay, with that trend, can you predict for these that I highlight, how many valence electrons? Notice what I said. How many valence electrons were those guys in yellow have? Based on what I just told you about the first column.
2.
Got it. Exactly. On the outermost shell. So Be beryllium has 4 electrons. Its outermost shell will be full with 2 electrons, 2s2. Okay. And that's what happened many years ago. And so magnesium has 12 electrons, and it has those 12, 2 of them are in the outermost shell, and so on down the road. Okay. And they have very similar reactivity. Now, I don't know if anyone's ever heard of Chernobyl. What happened there? We had a pretty bad meltdown of a nuclear reactor.
Oh yeah, I know pretty much all about that.
Okay. Well, it left a lot of radioactive material out in the atmosphere. And one of them is AR here, RA, excuse me, we're very radioactive. But it has 2 valence electrons, so its reactivity is very similar to calcium. So that material got into the atmosphere, got into the grass, cows picked it up, cows got it into their milk. Milk, who drinks milk? Babies and people. And so that radioactive material, because it contained very similar properties of calcium, got into her bones and all kinds of problems. Okay, so the other thing. Now, let me ask you to predict based on what you get. You're going, you guys are doing good now. I'm going to do one more prediction. Okay. For these elements here that I'm going to highlight, maybe right there. Okay. How many valence electrons do those guys have? Everybody in group 7.
7.
You got it. See that? You see? Pretty straightforward, huh? That Roman numeral tells me how many valence electrons. So if we take fluorine, for example, it's got 9 total electrons. Of those 9, 7 of them are on the outermost shell. Now the drive, the ultimate drive, we're going to learn this, is when chemical reactions occur, the ultimate drive is to get the happy 8, as they call it, or the octet. The drive is to get 8 electrons around the outermost shell. Right now, everybody here, the fluorine, the chlorine, the bromine, they got 7. They need 1 more. So they have a tendency, instead of losing those 7, they pick up 1 more. And by picking up one electron, now they got the outermost shell fulfilled, and they pick up a negative charge. Okay. And so that's the driving force for these guys over here on the right side to want to gain electrons. Whereas with metals, the ones specifically group 1 and group 2, when they lose those electrons, then they become like the noble gas as far as the electrons, like the noble gas behind it. But much more about that later on. It's all driven by the electrons and trying to be in the stable state as much as possible. And so we were here, and I lost my. Okay, so I started with hydrogen with one arrow, one electron represented by one arrow. Then we went to helium. Then we went to lithium at 3 electrons. Notice one in its valence shell in the 2s. Remember, the valence shell is the outermost electron. And then as I go across the periodic table is beryllium, next its neighbor, number 4. So now that's where I put it. Remember going across the periodic table, 2s2. Now, as I shoot across to boron, okay, boron is number 5. And remember on the periodic table, I said, think of these guys as the p elements, and that's where you start filling the p orbitals. And so guess what? This is boron, okay, number 5, element number 5. And then right next to it is carbon. Now I don't put the electrons in the same box. I fill up each orbital first before I start doubling up. So guess what? Look at carbon. As I find its position on a periodic table, it is in 2p1. The arrows represent 1 electron. Okay, that's what's representing. So right now I have a total of 6 electrons. 2 of them are partnered up already in the first level. Then in the second level, the first orbit is partnered up, 2 of them. And then I go across the periodic table with carbon, and the carbon's in the 2p column. Okay, so I got 2 electrons. And so I keep moving across the periodic table until I find all the way across. I'm going to fill them up here. When I keep going across the periodic table, I get to neon. Neon is number 10, element number 10. It's got a total of 10 electrons. Okay. What group is neon in? The last column is in group 8. It has 8 valence electrons. Guess what? They're in the second level. Isn't there 8 valence electrons in the second level here? Right? 6 of them in the p are full, 2 of them in the s orbit are full. I got 8 valence electrons. So that's why neon, for example, won't react anymore. It's full. It's got that happy 8. Now for neon, I go around the periodic table to sodium, and that's in group 3. Sodium's in group 3. And so I put its electron. Oh. Lost my electron. So sodium has 11 electrons, right? And it's in the first column. Remember we just talked about first column? Everybody has 1 valence electron all by itself sitting there, and it's designated right here. 1 electron sitting all by themselves, okay, in the third level. Now everybody has that. Everybody in group 1 has 1 valence electron. Where that 1 valence electron occupies depends on what energy level. Sodium's in group 3. Potassium next one down would be 4. So its valence electron would be in the 4th energy level. Okay? And we continue filling them up as we go across from left to right. So all right. So earlier I said that these orbits come from mathematical equations that once you plot the data to these mathematical equations, it gives you a picture of what these orbits look like. And so what has been defined as is that once we plot them, they look something like this, which kind of represents the probability of an electron being anywhere in that colored area. Obviously, the darker area means the probability is higher. The thinner area, probability is lower. So it could be possible. We don't know for sure that there may be sub-levels within that level where the electron is occupied. Okay, but the general shape is round, so the s orbits have a spherical shape. The p, there's 3 of them. Remember I mentioned that? For the s, there's one s orbit. There are 3 p orbits. Each one can handle 2 electrons. Okay, so we got 3 p's in x, y, and z position, and they had this kind of, we call it the dumbbell shape. Okay, after we plot the data, you get that shape, and that represents where electrons would be, at least 2 per orbit. So that's why you can get a total of 6, 2 in each x, y, and z. Now, we won't have pictures of the D and the F. We're not going to talk much about them, but the picture, that link, I couldn't get it to work anymore. I got to find another link, but the D and the F orbits are some really crazy looking orbits. It's beyond the scope here. They kind of look like futuristic space stations, some of these. So anyway, now I was going through the box of doing what we call the electron configuration. That shows you where the electron is with respect to the element. Now, there's 1 or 2 ways to do this. You can follow the order given here in blue in this diagram, where you start with a 1s, you fill that up first, then you move to the 2s. The coefficient in front of the letter represents the energy level. And obviously the lowercase letter represents the orbit, okay? And then in that lowercase, you're going to have a superscript. If it's S, the maximum you can put on there is a 2. If it's a P, the maximum superscript is a 6. If it's D, D as in David, lowercase d, is 10. And F will be 14. Okay, so the superscript represents the number of electrons. Okay? So you can use this order or this diagram to help you out. Or alternatively, you can simply find its position on the periodic table. I tend to prefer the periodic table because, I don't know, I just prefer it. I mean, you're welcome to memorize whichever works best for you. Okay, but I'm going to do an example, and then I'm just using the periodic table. Okay. All right, well, let's select an element, and let's do sodium. All right. Okay, so let's select. So based on the periodic table, we are going to do sodium, and let me highlight this first different color. Let me mark where sodium is. Sodium is right here, number 11. Okay, and so we have 11 electrons to work with. Second of all, I look and see where it's at. It's in group 1A. So that tells me that I'm going to have 1 electron all by itself sitting out there, specifically in a third energy level, the 3s1. All right, so that means that with the third energy level, that the other 10, the first energy level is full, and the second energy level is full. Okay, and so starting off with the first one. Oh, come on. My mouse is acting up here. My first one is I go across the periodic table since it's full, so I'm going all the way to helium, and that's simply 1s superscript 2. Okay, that's 2 electrons. So left to right is full. So that electron configuration is full. Now I come back to the second energy level. I'm going across the periodic table. Okay, so the s electrons are full. So the 2s superscript 2 is full. I'm going across them, and right now I'm in beryllium. That's what would be if you were looking for beryllium. That's what you would stop. Then we shoot across to group number 3A for boron. Remember, those are the P elements. So we got P1, P2, P3, P4, P5, and P6 to neon, all the way across. So we're still in the second energy level. So that's 2P superscript 6. Okay. Then we wrap it around to energy level 3. Okay. And it's in the first column in the S element. So it'll be S superscript 1. Okay. And the valence electron, remember, it's in group 1. Of those 10 electrons, 11 electrons, one of them is outside, out there all by itself. It's in the 3s1 orbit, in the third energy level. Okay. And so very quickly we did magnesium, excuse me, sodium. Now, if we needed to do magnesium, well, guess what? Keep all that. And I'm going to highlight this. Let's say we need to do magnesium, which is the neighbor X, which is right there, as 12. Well, all we got to do is change that 1 to 2. And that would be the electronic configuration for magnesium. All right, well, let's shoot across. Let's keep going to aluminum, number 13. We erase that. And we'll continue to highlight this so we know who we're looking at, 13. Okay. Well, now, since I'm already done with the S electrons, I'm still in the third energy level, but now I've entered the P element range. So it's 3P superscript 1. And there. And you continue across the periodic table. Silicon will be sp2. Phosphorus would be 3sp3. Sulfur would be 3p4. Chlorine would be 3p5. And then argon, the last one, 18, would be 3p6. So that's what I mean by using the electron configuration, using the periodic table. We're determining the electron configuration for these elements, okay? And you're more than welcome to utilize the periodic table or memorize the 1s2, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, etc., etc., etc. You can do that. Okay. Do at least the first 20 configurations, okay? See if you can do that. All right. Now, what happens is the 3D. Notice in this configuration, you get the 4S, and then right after the 4S, you get the 3D. That can be a bit confusing. What's the deal on the 3D? Well, to do that, to explain that, let me go back to the periodic table. Now, you don't have to worry about any of the D's until you start off with number 21. Number 21 is right here. Okay, those are the D elements. So the first 20, you just need the 4S, that's it. But once you hit the number 21, and if you went all the way across the zinc, then you got to worry about the D's. Now, you would think that the D's being in period 4, that it would be 4D, okay? 4D1, 4D10 all the way across. You would think that would be the case, but it's not the case. And this is why. The energy level of the D orbits are really one energy level in then from their respective period. So the D's for those elements in the fourth period actually begin with the third energy level. So this would be 3D1 for number 21. And if we shot across to zinc, that would be 3D10. And then you shoot back to the P starting with number 31. Okay. So for the D's, for the D orbit, if we need them, they're not in the period you would believe them to be, but they're in one period in. So subtract one from the period it's in. So for number 39, for example, it would be 4D1 because it's in the fifth period, subtract one. Okay. And that's because of the mathematics in the quantum mechanics and so forth. Now, the other thing that could be confusing would be the F. So if when you start number, if you ever need to start number 58, okay, that's where the F elements begin. Being in the period number 6, you would think, oh, okay, it's going to be 4F, but that, unfortunately, that's not the case. So for the F orbits, they begin 2 energy levels in than the period they're in. So it would be 4F rather than 6F. Okay. But you don't need to worry about them until you hit element number 58. Other than that, if you're not at element 58, then you don't worry about the F's. Okay. Because you're simply not at that element. And we're not going to do much on the F as far as electron configuration. So if you got the first 20, you won't have a problem. In fact, we can show you how quickly you can do number 20, which is calcium. Just let me clear it out. Just by knowing where it's at. Calcium is number 20. Okay. And the other aspect you hopefully recognize, it's in the fourth period. Okay. So just being in the fourth period tells you, and it's in column 2, that the outermost shell 4s2 is full. Okay. So we're going to write it longhand, and then I'm going to show you a shorthand way to do this. And so to do electron configuration for calcium, obviously we start off with the first 2 electrons, and level 1 is full. So we got 1s superscript Q, right? All right, so that's going from hydrogen across to helium. We wrap it around to lithium position. That's the second period, and that's full. So it's 2s superscript Q. They're shooting across the boron, all the way across the neon. So that fills up 2p6. Okay. So you should have 10 electrons, 10 superscripts up there. I got 6 from the P, 2 from the S, and from the 1s and the 2s. So I got 10. So I'm at 10 electrons right now. All right. So now I'm in neon position. I got to wrap it around, and we're at number 11, electron 11. We're going to fill that up. So that's 3s superscript 2. And we're shooting across to aluminum, all the way across to argon. So that's from 13 to 18. So that would be 3p superscript 6. So all those electrons are done. And now we are at argon position, 18 electrons right now. So we're going to go wrap it around. We're now at the 4th energy level, 4s superscript 2. So we wrapped it around 4s2. So we should have 20 electrons up there. Check my math. We got 4, 10. Yep. Okay. So that is what we call the electron configuration of calcium. Now, a shorthand way to do that is to stick calcium Okay. That is the longhand. Shorthand is we find the element that we're looking for, which I got circled already, calcium number 20, and we go back to the very first gas, which is in group 8, is there. And we go back to number 18 and we write the bracket AR bracket, not the parentheses, but the bracket. Okay, that represents the first gas that's behind it, what we call noble gas in group 8, which is argon, number 18. And now we just put in the 4s2. Okay, and this is the shorthand method of doing the electron configuration. Now, unless the question says don't use the shorthand, I don't have a problem with you using the shorthand to describe the electron configuration of any of the elements, okay? But if it doesn't say that, then assume that it's asking you to do the longhand method. Okay. Now, if, for example, we wanted to do number 21, we're at 20 now, but let's just say, for example, we wanted to do 21, okay, in shorthand. I mean, remember that's the D, and we subtract the 1 from the period it's in, and 3D of 1. Okay, and that would be the electron configuration for number 21, the one right after argon. And for number 22, guess what? 3D 2. And if we go on all the way across, and let's say we wanted to go to zinc, which is number 30, guess what we do? There it is. 3D. Okay. All right, and so forth and so forth. Where are we at? All right, so this is an example of the electron configuration we just did for carbon. So find its position in the periodic table. We can use the periodic table or just use this 1s, 2s, 2p method of filling it up. Keep remembering that the S can only handle maximum of 2, and the P's can handle a maximum of 6, the D's 10, and the F's 14. Okay. Now, you might be asked a question. All right, for energy level number 3, right here, what is the maximum number of electrons that I can put on the 3rd energy level?
Is it 18?
18? Okay, how'd you get 18? It's correct. It's correct.
I was looking at the last element, which is argon,
Yes.
for level 3.
Okay. But don't forget, you can also put in the 3Ds come into play in the 3rd energy level. So the S's can handle 2. The P's can handle 6. Okay. And then the D's handle 10. So yes, that would be 18. Maximum number of electrons for the 3rd period. Not to be confused if you're asked what is the maximum number of electrons I can put in for the F orbit. Now they're asking specifically for the F orbit, which is 14. Okay. Or for the D, which is 10, and for the P, which is 6. All right. For the 2nd energy level, the maximum, what is the maximum for the 2nd energy level? At the 2nd energy level, what is the maximum I can put in?
$10?
10? Oh, sure. We're talking about okay. Okay, one way to do is to go back and look at this. This might help at that pyramid right here. On the first energy level, the maximum we can put in is 2 electrons. The second energy level, the maximum we can put in will be 6 in the P, 8, exactly. So, and then the third energy level, the maximum we can put in will be 18. And the fourth, you can see the maximum we can put in because the F's come into play. So we're gonna add 14. So we got 14 and 10 and 6 and 2 for the fourth energy level. Okay. Yeah. So be careful when you read the question if they're asking about the level or they're asking about the orbit. Okay. There's a different answer for the question, obviously. All right. So if we're going to be doing the electron configurations, we did the sodium, but this is you can see sodium here: 1s2, 2s2, 2p6, 3s1. Sodium is in group 1. Okay. And if you look at this, remember the outermost shell is the valence electron. That is where all the stuff is happening. This is where all the chemical reactions occur. So for sodium, that one lone electron will occur on the outermost shell. That's the outermost layer of the onion for sodium, if you will. Okay. For oxygen, it's got 6 electrons in the outermost shell. Okay. For calcium, its outermost shell is in the 4th energy level, has 2 of them. And for chlorine, its outermost shell, valence shell, has 7 electrons. Now, here's something interesting when you think about it. For metals like sodium and calcium, they rather lose those electrons in the outermost shell because then when they lose them, what happens? When they lose these shells right here, like that, and like this, in other words, they're empty, the electrons are gone. Look at the next layer in now. It's full. For calcium, it's a 3s2 and a 3p6. 6 plus 2 equals 8. For the sodium is the 2s2, 2p6. 6 plus 2 equals 8. Now, the nonmetals like oxygen and chlorine, look at their valence shell. They got a total of 6 electrons. That P has room for 2 more. And the P for the chlorine has room for 1 more. So they rather would lose gain. Oxygen would rather gain 2 electrons to fill in those 2 missing orbits in the 2p range, in the 2p level, and chlorine gain 1 electron. And so chlorine gains 1. Now look at the outermost shell. Now it's full with 6, 8. 6 from the P, 2 from the S. For oxygen, same scenario, 6 in the P, 2 in the S. Okay. So these nonmetals have a tendency to gain electrons. And by gaining electrons, it fills up the outermost orbital up to get that magic 8. The metals can have a tendency to lose electrons because the next layer in now is full, and that's fulfilled, and it has the octet. Okay. The driving force is to get that octet fulfilled. All right, so I got 5:30. So let me stop it here on page 20, slide 27. And we'll continue on Thursday.